Now that we've tried simulating DFS on an actual graph, let's jump back to the source code. So some of the stuff that's here we've already seen a bit, but now what you're seeing is the entire implementation of that search problem from earlier. So this is kind of our whole thing. So we have here in Write Magic, this is basically a class. This is what we would have. So we have basically two variables inside of it. So we have something for marked, we have something for count. Then we also have a constructor, right? And so our constructor is basically our setup. Our constructor is keeping track of, what is the graph that I'm looking at, what is the starting place. So in here, right, basically what I'm doing is I'm setting up, right, my marked node, right, to basically be a whole bunch of blanks, right? So I want to have this blank Boolean array that basically has everything set to equal to false because it's like, well, I haven't seen anything at the beginning of time. And then what I have, right, is I run the actual DFS algorithm. And this is actually a snippet of code that we had a couple of videos ago. So this is the heart of the algorithm over here, right? This is our DFS. And what we're doing there, right, is we're basically having that embodiment of the algorithm where it's like, well, I'm going to mark it, count it, and then look at its neighbors and recursively go and visit everything, right? So this is the process we just practiced using, right? You can see it's kind of laid out there. There's nothing particularly new here. Now on the bottom part, right, we have two really simple functions just for marked and then for count, right? So the kind of the assumption here, right, is that you run into this, right? Well, I should say you create an object, right? Constructor runs. When the constructor runs, it basically does the DFS, right? So everything's been set up. And so later on, if you want to ask, are two things connected? Well, then you can call this marked thing. And the marked method will, of course, look at that array and basically say, oh, hey, is the position they're asking about, is that something that the index has been set equal to true or not, right? If it has, it'll return that true, otherwise it returns false. So kind of it's almost as if you're catching the results ahead of time, right? So rather than checking to see whether something's marked when you call the marked method, you basically run DFS at the beginning, mark everything that is reachable, and then just look it up later. Last thing we have is, of course, count, right? So count is basically going to be us, checking to see how many nodes were reachable from that very first one. So yeah, this is our source code. All in all, it looks really, really simple. So one big note here, right, of something that hopefully you got a little bit from the previous trace we did of this, is the fact there's actually a lot of work being done by the stack, right? So there is actually a stack here. It's not in the code, right? I'm not creating a stack object or anything, but there is a stack here, right? The stack I'm talking about is, of course, the call stack. So remember in the previous diagram, I was doing stuff like drawing, DFS as being indented, right? So I would do things like DFS, of 0, then DFS of 1, DFS of 2. That indent is showing me that I'm making recursive calls, right? So one DFS call is making another DFS call. Well, the way calls are managed in the operating system is via the call stack, right, which is a stack-like data structure. So basically what happens is you're getting a stack for free, right? So it's as if you are basically getting to manage where you are in the graph. So this is actually going to be kind of a very kind of nice feature for us. If you go back and think about the trace, you can kind of visualize yourself, right? In the trace, right, it's like I was moving through the graph and I would maybe get to a point which is like a dead end. Well, when I was done with that, I basically unwound myself. I went back to the previous place and then I started going through a new path, right? So it's like I didn't really get stuck. And that's actually being enabled by this kind of this stack implementation, right? So stack implementation means that as I'm moving through my graph and making more calls, if I get to a call that doesn't go anywhere, I just complete, I return from it, and it goes me back to the previous call, right? So if DFS of 2 has nowhere to go, it rolls back to DFS of 1, and maybe DFS of 1 can make another call, right? Because it's still kind of on the system's call stack. So I have basically the chance to maybe go somewhere else, right? Or if maybe there's nowhere to go from 1, then I rewind all the way, right? So maybe 3 rewinds to 1, 1 rewinds to 0, and then from 0, right, maybe I make another call, right? A DFS to something like 4. So I have basically the stack mechanic, right? I'm pushing on calls to DFS as I explore deeper in the graph, and then when I don't go anywhere, right, I don't get somewhere good, I'm popping them off, right? I'm backtracking, I'm going somewhere else. So it's like here, you could almost imagine, right? You have something that looks like a stack, right? This is the call stack now. And you start with DFS of 0 at the bottom, right? Our first call over here in this diagram. And then we do DFS of 1 is kind of thing on top of it. DFS of 1. DFS of 1 calls DFS of 2. Right? This is kind of on the call stack. And it's like, well, 2 is a dead end. I don't do anything, right? So maybe I don't do that. Then I could put like DFS of 3 or something like that, right? Maybe that's a dead end and I erase that as well. Then I erase 1. And then I go back and I put DFS of 4, right? So somehow, right, that call stack, right, is basically giving me a stack-like data structure for tracking where I am in exploring this graph, right? So it's letting me basically do my backtracking. So it's not really visible here in the code, but we do have it just because there's a recursive call. Recursion, right, means that we are pushing on extra calls onto that call stack and keeping track of the places we've kind of already been. Remember that when we return from a function, right, say we have some calls, right, we get to the end and we want to come back, we basically go back to the state of the function before we made that call. So if we're like in the middle of the loop, well, we're going to resume that loop, right? We're going to continue exploring the rest of the neighbors. We're not going to restart. We're just going to go back to where we made that call from. So just keep that in mind. So yeah, so a lot of the functionality here, right, is basically coming from that, using that stack, right, in terms of the recursion, right? A lot of the complexity is there. And because of that, right, we get this relatively straightforward code. All right, so that's it kind of for talking through the code a little bit. In the next video, we'll spend a little bit of time just doing one more kind of graphical simulation of how this thing runs through data.